Okay, so now we're going to take a look at Charles's law. Jacques Charles lived in 1746 to 1823. He was a French scientist and determined to understand the relationship between temperature and volume. Just thinking about it, close your eyes. If you have particles at a certain temperature and you increase the temperature, what's going to happen to the volume? So, for example, if you have a balloon and you blow up a balloon on a very cold day outside and you bring it inside, the balloon will probably increase in size and volume because the gas particles are now moving faster inside of that volume. He found that for every increase in temperature, all gases expand by the same ratio, provided that the pressure and the amount of gas remain constant. And he determined that graphically, if a gas does not liquefy, its volume would become zero at negative 273 degrees Celsius. So we talked about this number before, and this is at 0 Kelvin. Lord Kelvin reasoned that at 273 degrees Celsius, molecular motion would cease. So kinetic energy would be zero, and so the volume of the gas would hypothetically also be zero. He used this as the basis for his new temperature scale and was called the Kelvin scale. Again, all the temperature that you're now going to be using will be converted into Kelvin. So how would you do that? You take your degrees Celsius and add 273. So starting point for Kelvin is 0 K, negative 273 degrees Celsius, or also called absolute zero. So here's just a graphical representation. So here, this is the volume of the gas. So as temperature decreases, the volume of the gas also decreases with the same amount of pressure. So this little object here is a little weight indicating the same amount of pressure on both of these. But as the temperature decreases, you'll see that there's a decrease in volume. And then here is just the point in time where the motion will cease. So as the temperature increases, volume increases. Okay, and as temperature decreases, volume decreases. So let's take a look at the formula. It's V1, where volume 1 is the initial volume, and VT1 is the initial temperature. And the same for V2. So you can either memorize it this way or this way. This way just seems more simpler for me. The V1 over T1 equals V2 over T2. But this way it's easier to do the substitution in your math calculations. Okay, so again, please remember to convert all of your temperature from degrees Celsius to Kelvin. And to do that, you're just going to add 273. Okay, so imagine the air in your bike tire. After a cold night, your bike tire will have cooled down and will be a little squishy. The tire probably hasn't lost any air, but the cooler night temperature, the volume has decreased. Later in the day, once the air in the tire heats up, you increase the volume because the temperature has now caused the particles to move faster, increasing the volume. And again, same here. An air balloon, it's not that there is more air in this balloon, it's just that the particles in this balloon are now moving faster because of the heat. The temperature has increased by this flame on the inside of an air balloon. Okay. Charles's law becomes important when filling a scuba tank. So when you're in the tropics, normally they take a scuba tank and fill it in a fridge because in order to put the maximum amount of air into the tank. So think about it, if they did it outside in the scorching hot sun, they wouldn't be able to put as much air into the tanks because of the heat. So as a result, scuba tanks are often filled in cold water baths. Okay, so let's take a look at a sample question. If you 100 liter of oxygen gas at 25 degrees Celsius is cooled at a constant pressure in preparation for storage, to what value must the temperature be lowered before the volume is reduced to 1/4 its size? Okay, so this is a little tricky question. You have, so our volume 1 is 100 liters. And it's at 25 degrees Celsius. Now I need to convert that to Kelvin, so I'm just going to add 273. To what value must the temperature be lowered before the volume is reduced to 1/4? So I have to times it by 1/4, gives you 25 liters. And we want to know what temperature that would be. So here is our formula. So like I said, this one's just easier for substitution. So we want T2 by itself. So let's substitute in our numbers. And liter cancels out, so we end up with Kelvin. So make sure you always put your units in your calculation so that you can cancel them out. And know that you have the right unit here. Okay, so the sample must be cooled to 74 Kelvin, or 74 minus 273 gives you minus 199 degrees Celsius. Okay, so tomorrow in class we'll work on worksheet 3.